guys, this is Mrs. Harbin, and this is Pre-Cal. We are in Chapter 5, and today we are looking at 5.7, double angle and half angle identities. So we are continuing with our long list of trig identities here, and we're going to use all of these to help us solve trig equations in the following lessons. But first, let's take a look at our biblical correlation. Our verse for this unit is Ephesians 6:10 through 18, and this is just a quick synopsis of that. But finally, be strong in the Lord and in his mighty power. Put on the full armor of God so that you can take your stand against the devil's schemes. And we're reminded that we have all of these little pieces and parts that God gives us to help us solve or tackle bigger problems. When we're learning to read, we have to learn the letters first, and then we have to learn how those form words, and we learn piece by piece until we're able to tackle more challenging material. You guys are starting to learn these beginning pieces of trigonometry and trig identity so that you can tackle bigger problems in the future, and life is similar to that. God gives us the things that we need to tackle these bigger problems that will face us as we go through life. Our lesson objective for today is that you, the student, will evaluate and prove trig functions using double angle and half angle identities. So let's take a look at the double angle identities. You can see the proofs for these on page 258, and we're actually going to do some of the proofs in class. But if you're just wanting to know the identities and how to use them, so cosine of 2x or 2 cosine x, you can see it written either way. We can substitute or write that as cosine squared x minus sine squared x. Cosine squared x minus sine squared x. One derivative of this, using the Pythagorean identity for sine and cosine, we can rewrite that as 2 cosine squared x minus 1, or 1 minus 2 sine squared x. Now, I'm not going to show you how we derived these. These are actually on page 258 of your book, but these are derivatives or applications of the Pythagorean identity from sine and cosine that allows us to write this double angle identity for cosine 3 different ways. The double angle identity for the sine function is 2 sine x cosine x. So just the one identity there. So make sure that you have these written down on your identity note sheet, and you recognize as you're proving trig problems here, trig identities, that these two double angle identities can be written as these various ways. Now a half angle identity looks like this. The half angle identity for cosine is cosine x over 2, so cosine 1/2 x, equals plus or minus the square root of 1/2 times 1 plus cosine x. And the half angle identity for sine is sine 1x over 2 equals plus or minus 1/2 times 1 minus cosine x. So the half angle identity for sine is actually written in terms of cosine. There's a negative cosine here. And the half angle identity for cosine is also in terms of sine, but with a positive cosine x. So let's find sine equals pi over 2. The first thing that, or pi over 8, I'm sorry, the first thing that we want to do is rewrite pi over 8 as a half angle. So if you're not sure how to do that, let's think pi over 8 is the same thing as what over 2. And if you cross multiply and then solve for x here, you get x equals pi over 4. So pi over 8 is the same thing as pi over 4 over 2. So we're going to rewrite that first as a half angle. So sine of pi over 8 is the same thing as sine of pi over 4 over 2. We'll then apply the half angle identity for the sine function. So using our half angle identity, we get 1/2 and then 1 minus cosine x. This number right here, this is our x. Remember, it's sine of x over 2. So whatever's in our numerator, which in this case is pi over 4, is our x, and that's what gets plugged into our formula here. We'll then make substitutions. So we know that cosine of pi over 4 is root 2 over 2. And we'll distribute, we'll multiply to get rid of those parentheses. 1/2 times 1 is 1/2, and 1/2 times root 2 over 2 is root 2 over 4. We'll find a common denominator, so we'll write 1/2 as 2/4, And then after we've written that as 2/4, we can simplify that. So we have 2 minus 2 as our numerator and a common denominator of 4 on the bottom. We can then simplify that yet again by writing that as square root of 2 minus square root of 2 over the square root of 4. The numerator can't be simplified, so it stays as it is, root 2 minus root 2, all over, and then the square root of 4 is simplified to be 2. So this is our final answer. That is the sine of pi over 8. If we were to plug that into our calculator, we would see that that answer in decimal form would equal the same thing as if we plugged this in decimal form. But remember that decimals are not as precise as keeping things in this form, because we do have to round off our decimal form, eliminates the rounding, and it is more precise. Let's go ahead and do another example and prove cosine 2x equals cosine 4th x minus sine 4th x. Okay, the first thing that we want to do is on the right side, we're going to select the right side and we're going to factor it. So if this was x to the 4th minus x to the 4th, for example, or x to the 4th minus y to the 4th, we could rewrite that as x squared squared minus y squared squared. And that's just a difference of squares. And our difference of squares pattern says we can take the square of the first minus the square of the second, and then our second factor is square of the first plus square of the second. So that's square of the first minus square of the second, square of the first plus square of the second. That's our difference of squares pattern when we are factoring. Okay, once we have factored that, we can apply the Pythagorean theorem, because we know that cosine squared plus sine squared is 1. That leaves us with cosine squared x minus sine squared x, because when we multiply that by 1, we're just left with cosine squared x minus sine squared x. Then we're going to apply the double angle identity for cosine. If you remember our double angle identities, we said that cosine of 2x is the same thing as cosine squared x minus sine squared x. So we can apply the double angle identity and just rewrite that as cosine 2x. And if you remember back at our original problem, we were trying to prove that cosine 2x is equal to this. We were able to simplify that, and now our left and our right hand sides match. Cosine 2x equals cosine 2x. All right, let's try another identity. Let's prove that cosine 2x is equal to 1 minus tangent squared x and 1 over 1 plus tangent squared x. The first thing we want to do is start with the more complicated side, and we are going to go from there. Using our quotient identities, we can rewrite tangent squared as sine squared over cosine squared. So we're going to do that to both the top and the bottom. Now this is a complex fraction, so we can simplify this complex fraction and rewrite that as cosine squared x minus sine squared x over cosine squared x plus sine squared x. Once we have that complex fraction simplified, we can apply the Pythagorean identity, because we know that cosine squared x plus sine squared x equals 1. And cosine squared x minus sine squared x divided by 1 is just cosine squared x minus sine squared x. And using our double angle identities, we know that cosine squared x minus sine squared x is the same thing as cosine 2x. It is our double angle identity. So we were able to use quotient identities and the Pythagorean identity to prove that cosine 2x is equal to 1 minus tangent squared over 1 plus tangent squared. All right, I'm going to do that very quickly. You do need to make sure that you learn those double angle and half angle identities, have those written down on your identity sheet, and get used to using those and practicing using those. Today we did these things. We evaluated and we proved trig functions using double angle and half angle identities. If you guys have any questions, be sure to write those down, and I will see you next class.